This question says, find the x-intercepts and the y-intercept of the function. And our function is f of x equals 9x squared minus 4x minus 2. I'll find the y-intercept first. To find the y-intercept, you're going to let x equal 0. So we're substituting a 0 into our function. That would give me 9 times 0 squared minus 4 times 0 minus 2. 0 squared is 0. 4 times 0 is 0. 9 times 0 is 0. Negative or minus 0 and minus 2 combine together to be minus 2, and 0 minus 2 is minus 2. We have a y-intercept at 0, negative 2. Then we'll find our x-intercept. To find an x-intercept, you let y equal 0. And the y in this example is f of x, capital F of x. That is our function notation. So we're going to let capital F of x be 0, and that would give me 0 equals 9x squared minus 4x minus 2. And I might try to factor this first. The numbers that go in this position and this position would need to multiply to be 9x squared. So that's, I have some choices for factors of 9. That's 1 times 9 and 3 times 3. So I'd probably try 3x and 3x first. The numbers that go in this position and this position need to multiply to be negative 2. I only have one choice for factors of 2. That's 2 times 1. So I'd do 2 and a 1, and I would test out the inside and the outside because I want to make sure that I would get the right middle term. So for the inside and the outside, that would be a 6x and a 3x. And if I combined 6x and 3x by either adding or subtracting, that's not going to create a middle term of 4. So I know this is not the right choice. Normally, I would say we would switch the 2 and the 1, their position. But since our beginning numbers are the same, switching the 2 and the 1 aren't going to give me a different combination. So I need to switch my front numbers and try 9 and 1. So I'll try a 9x and an x. Once again, testing the inside and the outside. That would be 2x and 9x. If I add and subtract 2x and 9x, that's not going to create the middle number of 4x that I need. So let's try switching the position of the 2 and the 1. And for my inside and outside, that would give me x and 18x, and once again, that's not giving me the middle term of 4x. So I've tried every combination of factoring and it doesn't work. So I'm going to rely on, instead of factoring as the method to solve this quadratic, I'm going to try the quadratic formula. And the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. A, B, and C are referring to the coefficients in my equation. So for this example, and every example, A will be the coefficient of your x squared term. So that's 9 for this example. B is attached to your linear term, which for this example is negative 4. And C is the constant, which is negative 2. I'll substitute these values into the quadratic formula, which will give me negative b plus or minus the square root of negative b squared minus 4 times a, which is 9, times c, which is negative 2, all divided by 2 times a, which is 9. Then I'll begin to simplify this using order of operations. So negative negative is positive. Negative 4 squared is a positive 16. And then I have 4 times 2, which is 8, times 9, that's 72, all over 18. Underneath the radical, I'm going to add 16 and 72, which would give me 88. And then I want to try to simplify that radical. And when I simplify the radical, I'm looking for perfect squares. So I'm looking at factors of 88. That's 1 times 88, 2 times 44, 4 times 22, 8 times 11. So we want to choose this factorization because 4 is a perfect square. 4 is 2 squared. That's going to allow me to simplify the radical. So that's 4 times 22 underneath the radical. And we're able to do the square root of 4 times the square root of 22. So we've applied that radical to each factor. The square root of 4 is 2. And 22 is not a perfect square, so I'm not able to simplify that anymore. And the last thing that I can do here is anytime you have fractions, you want to try to reduce them, write them in lowest terms. You don't want any factors in common between the numerator and denominator. And as I look at this numerator, I can see that these two terms are even and this term is even, so that means that they'll have a common factor of 2. I'll cancel out that factor of 2 from 4 and from 2 and from 18, and that's going to leave me with 2 plus or minus 1 square root of 22 over 9, and 1 square root of 22, that's 1 times square root of 22. And 1 times anything is itself, so we can get rid of that 1 there. So we've found the x-intercepts to be 2 plus square root of 22 over 9 and 2 minus square root of 22 over 9. I'm going to kind of zoom out so you can see all of the work at once. This question says, use the graph to determine the domain and range of the function. When I find the domain and range from a graph, I like to use a ruler or a pencil to help me. So to find the domain, I'm going to hold my ruler vertically. And the reason why I'm holding it vertically is because as I hold it vertically, it's marking spots on the x-axis. And that's important for domain because the domain is the set of all x values. So the domain is the x's. And so holding my ruler vertically will help me identify what x's I have on this picture. So I hold that ruler vertically and I'm going to go from left to right. And the reason why I'm going to go from left to right is because I'm going to write my domain in interval notation. And interval notation is always written from smallest to largest. And on your number line, smallest to largest goes from left to right. So I'm going to start on the left. And as I move across the graph from left to right, what I'm trying to take notice of is when my ruler first hits the graph. So my ruler first hits the graph at negative infinity for this picture. So I'm hitting the graph right here. I'm going to continue to hit the graph until we get to this vertical dashed line. This vertical dashed line might seem a little unfamiliar right now, but this vertical dashed line is a feature of this graph called a vertical asymptote. And it's an undefined spot on this graph. So just to be a little bit more clear, what's happening on this picture here is that you are getting closer and closer and closer to this line, but you're never going to reach the line. And so this provides a gap in the domain. So your domain is going to stop at this value, and that value, I can see it right here marked on the scale, would be -5. So my domain is going to stop at -5. And on that -5, because this is a gap in the graph, a breaking point in the domain, I don't want to include -5 in my domain. So there's a break in the domain right there at -5. Immediately after -5, you can see here at the bottom portion of the graph, the graph picks up right after that -5. So this is a break in the domain, but the break is just one single value, and that's -5. So right after -5, my domain starts again, and we'll continue until I get to this next vertical line. Next vertical dashed line is another vertical asymptote, and that's occurring at x equals 5. So you're going to have another gap in the graph, another gap in the domain that happens at 5. But then immediately after that gap, you have the graph picking up again, so that gap is only a single point. So your domain will start again at 5. And then there are no more vertical asymptotes, and the graph continues the rest of the way to infinity. So that's your domain. Then you want to find the range. And for the range, you're going to hold your ruler horizontally. You're holding it horizontally because the range is the y values, and this is going to mark out values on the y scale. So the range is the y's. And once again, we're going from bottom to top so that we can go from smallest to largest. So from the bottom, you can see we have arrows on this graph here, meaning that it's going to continue on down. And that means that our range will also start at -infinity. So as I go from bottom to top, I am touching the graph with my ruler all the way until I get to this little peak in the graph. That little peak in the graph is happening at a y value of 0. So my range is going to stop at 0. Now that point where the range stops, that point right there, is the ordered pair 0, 0, and that point is on the graph. So that point is included in the range. That's unlike what we had with the domain. With the domain, that was a gap in the graph, a break in the domain. Versus here, we have, instead of a gap, we have just a stopping point. The range stops at that value, and that value is included. Okay, so you can see with my ruler here that my ruler's edge is not touching the graph at all. and it doesn't start touching the graph again until after this horizontal dashed line. That horizontal dashed line is a feature of the graph called the horizontal asymptote. And once again, that graph is kind of getting closer and closer and closer and closer to that line without ever reaching it. So our range will start at 2. And continue on until infinity. On that 2 itself, we would use a parenthesis because this portion of the graph is getting closer and closer and closer to that value of 2 without ever reaching it. So 2 will never be a part of the range because the graph never reaches 2. So we have our domain and range of this function.